Yes, welcome you all for another presentation on the very important and very interesting and most beautiful subject of electronics background is random variables and random processes. This is the very important subject. Actually, it will be very useful as we are discussing since long back, and in the estimation of the noise which is present in the communication. In order to estimate the characteristics of a noise, basically these random variables and random process subject will takes very important role in that aspect. Right. In today's presentation, by the way, it is a lecture number 7, which we are going to see today. In this presentation, just I would like to brief you some of the very important properties of probability distribution function and probability density function. So, in the last presentation, if we recall, we have seen the definition of a probability distribution function, nothing but the joint probability, the name itself here, as I mentioned here, joint probability distribution function as well as joint probability density function. What do you mean by joint? Joint is nothing but the joint means we need two random variables. We are considering as x and then y. These are the two random variables basically as far as your subject is concerned, and as far as your examination point of view and subject point of view. Let us uh, remember that only we will consider two random variables only, that is x and y only, not more than that. Okay, and can be extended to the n number of random variables, nothing wrong in that. Okay, just recall the definition. Actually, the definition, if you see the definition of a joint probability distribution function, right? So if you see the definition, joint probability joint probability distribution function, joint probability distribution function. What is the definition? This is nothing but actually capital F of x comma y, and if you take the small x and small y is equal to probability of the event capital X is less than or equal to small x comma capital Y is less than or equal to small y. This is the definition of a joint probability distribution function. So this f of xy, whatever we are writing here, this is called as joint probability distribution function. Joint means joint function, joint distribution function of random variable x and y. So within the bracket, if you see, what is the small x? Small x is nothing but the possible outcome value of capital X, means the small x corresponds to the possible outcome value of the random variable x, whereas this small y corresponds to the possible outcome value of the random variable capital Y. So small x is the possible outcome value of capital X, small y is the possible outcome value of capital Y. And this is the distribution function, this is the representation, okay, of the distribution, joint distribution function. And furtherly, this can be written as like this: probability of the joint event. This is called the joint event. The whole, whatever is there within this bracket, this is called joint event. Remember that. This is called joint event. This is the joint event. Actually, it is a subset of a sample space. this event, the joint event, whatever we are calling it as a joint event or simply event, if you see, as we have discussed, if you recall our first presentation of this, I mean probability or otherwise the random variables which we have started in our earlier presentation, as I have discussed you, as I have told you that if you consider this is the sample space, actually this is the sample space, okay, this is the sample space, nothing but denoted by S actually, and this sample space defines a certain experiment on the sample space, and for that experiment the possible outcome values are something like this: x1, x2, x3, and so on so forth, and so on so forth, x4, and so on so forth, like that. These are the possible outcome value of that experiment, and which is defined by the sample space S. Right now, just I want to give a functional relationship between the possible outcome value to the sample space, means it is the mapping. In order to bring the relationship between that, I am calling it as, it is nothing but capital X of small x. This is what the functional relationship actually. This is the capital X is the random variable and small x is the possible outcome values, where x you can write x suffix I, where I is equal to some 1 to n, no problem. Okay, right. Now so if I from this sample space, from this known information, if I define something like this, x is less than or equal to x, what is this? This is nothing but a subset. We are calling it as an event. That is the second definition. But first of all, see that this is a subset of the sample space. This is called a subset actually. It is a subset. It is a subset of sample space, and this subset it can also be called as an event. That is, remember that this is a subset of the sample space, right? And this subset is also called as an event, and that must be an event first of all, right? In order to be x is a random variable, in order to be x is a random variable, and this must be an event. This subset, whatever the subset we are calling this as, this subset must be an event. That is the very desired condition, that for any variable, maybe you can write x or y or whatever you like, capital X or capital Y, capital. I think you are getting what I am conveying. I think I am something meaningful, I think. Is it not? So, what I told you that random variable is a variable, or it is a functional relationship that gives between the sample space and to the possible outcome values of the experiment, right? So, in order to give that functional relationship, we are considering a new variable, that is what x actually, maybe x or y or z, whatever you write. Nothing wrong in that. These are what these variables I am calling as random variable, right? So the variable which I am considering as a random variable, it is not simply a random variable. I should not call it as a random variable unless it satisfies a condition. It must satisfy a condition, is that for any subset of the sample space, means that this is what the subset, that subset must be an event. That subset of the sample space must be an event with respect to that random variable x. Then only the variable x is called a random variable. Or if you write y, means that in order to, if you write for y in the same fashion, because I want to give little bit additional information for your more clarity. That's why. Do not get bored or I think. So, it is y and less than or equal to small y if you consider a random variable as y. Nothing wrong in that. Either you can consider z also. if you consider z as a random variable, then its possible outcome value must take small z. It is a small z. It is a small z. This is what are these actually? These are the subsets. These are the subsets of the sample space, and these subsets must be an event. This must be an event. It must be an event. Event means the experiment. Event is nothing but an experiment, and that gives certain values as output. That is what an event. Event. Okay, understood? So an event is nothing but an experiment through which you will get certain outputs. If you do not get any output, you never call it as an event. No. If you are calling it as an event, definitely it should produce certain outputs. That is what event means, right? So that is what the thing. And basically, this is the subset, and the subset must be an event. Then only the random variable y as well as the variable z and y are called random variables. Clear? That is what the very, very important condition. Now, again, coming back to our actual, topic of today's presentation is that, as we have seen, the joint probability distribution is nothing but a capital F comma xy in bracket. If you write small xy, that is equal to probability of the joint event, that is capital X is less than or equal to small x comma capital Y is less than or equal to small y. This is the definition. Remember that always. This is the definition of a joint probability distribution function. And also we have seen the joint PDF also. What is the joint PDF? What is the joint probability? Probability density. Probability density function. What is this? That is nothing but small f of x comma y, and then in bracket if you write xy, this is nothing but dou square by dou x. This is already we have seen in last presentation. Capital f x y in bracket x comma y. This is the definition of a small PDF, means probability density function. So these are the very, very important formulas. Must note down, must remember this. These are the very, very important formulas. Joint probability distribution, joint probability density function. This is the probability density function. This is the joint probability distribution function. This is the distribution. This is the density function. Right? Very clear. Now, let us see some of the very important properties of these two, distribution function as well as the density function. We'll see certain important properties. There are very, very beautiful properties are there, and which are very much helpful in solving the problem actually. Sometimes in the examination, one function will be given to you and you will be asked to determine whether the given function is a valid distribution function or not. Likewise, you will get questions in your competitive examinations. So remember that, right? Well, so let us see some of the properties, very, very important properties. So properties of, I can write, instead of writing everything, just I can write like this simply, f of x comma y and then x small xy. Okay, what is this? It is nothing but distribution function, probability distribution function. If I write like this, you can treat it as probability distribution function. Now, the very first property is that, the very beginning property is that, so see that, so here small xy values are the possible outcome values. These values can take either from minus infinite to plus infinite, right? So this x can take minus infinite to plus infinite as well as Similarly, this y can also take minus infinite to plus infinite. Clear? These are the possible outcome values basically. So this x can take its value because I am considering these x and y as continuous random variables. Remember that. So your random variables can be a continuous random variable, as well as your random variable x and y can also be a discrete random variables, right? Remember that. So if these variables are, means these x and y random variables are continuous random variables, then we will take the limitations from minus infinite to plus infinite. Clear? Both x and y values take the same limitations, right? In this way, I can write the first property as, means that the first property of the distribution function f x comma y, and if the values, if I take minus infinite comma minus infinite is equal to, clear? I think you are getting. So already I have explained here. So f of xy in bracket x small x and small y I am writing. What are the small x and small y? Small x is the possible outcome value of capital X, and that is defining over minus infinity to plus infinity. So here in this property, if I am writing the minus infinity for this x value, I am considering the lower limit, this limit, as well as for y, the second comma minus y is nothing but this is the lower limit of this y actually. Clear? So means that what actually, for this first property, I am considering my small xy values with their lower properties, minimum properties. So if you take if you take the distribution function over this minimum limitation values of x and y, this distribution function becomes 0. The distribution function becomes 0. Remember that. Okay, f of xy minus infinity comma minus infinity is definitely, it is 0. And similarly, not only this, remember f of x comma y, it is x comma y, and then if you write this, if you take minus infinity, as well as the second one as it is, you can keep as y, no problem, right? In first case, I am considering xy limitations are minus infinity, minus infinity. In this case, your distribution function becomes 0. Clear? And the second case, f of xy, so the x value I am taking, this is always remember that the first value belongs to x and the second value belongs to y. So in the second case, the first limitations I am taking as minus infinity, and y as it is I am keeping like this only. Again, in this case also, your distribution function f of xy becomes 0, right? Similarly, f of xy, and if you write this as x, you can keep x as x only, and y value if you take minus infinity, and again in this case also means, so the third case, so on the first property you will have 3 different cases. This you can call as number 1, and you can call it as number 2, and you can call it as number 3. 3 cases you will have actually. 3 cases. This is the first case, this is the second case, this is the third case. So in the third case, you can keep x as it is, and you can apply the limitation of y as minus infinity. In this case also, your distribution function, joint distribution function becomes 0. So from this property, what you can understand means that, so if the distribution function takes x and y values for different x and y values, if any one of the limit is minus infinity or both are minus infinity, any one, either x or y, in this case x is minus infinity, in this case y is minus infinity, in this case both are minus infinities. So if any one takes minus infinity or both takes minus infinity, distribution function is equal to 0. Very fundamental, very fundamental, very interesting actually. This is what the first property of the distribution function. I think you are getting. Now coming to the second property, similar only. Similar only. So if you see the second property, f of xy, so the second property same, in the same line I can write like this, capital F of x comma y, and here I can take plus infinity comma plus infinity, plus infinity comma plus infinity, or simply you can write, instead of plus infinity you can write f of xy. Simply you can write infinity comma infinity, nothing wrong in that. Either you can put plus, plus itself is plus only, it is not required to mention. So you can write like this, or even you can write like this also. In this case, it is 1. Your distribution function becomes 1. That is the second property. The distribution function becomes 1. Clear? So from this, what you understood actually means that, so the distribution function for the maximum limitations of x and y, maximum limitations. So these are the maximum limitation values of x and y. So for the maximum limitations value of x and y, the distribution function becomes 1. Therefore, by observing the first property, this is what, so combinedly these three collectively called as the first property, and this is what your second property. Therefore, if you observe from the first property and then the second property, you can say that the distribution function, means the joint distribution function f of xy, lies between 0 to 1. Means the joint distribution function lies, means it exists between 0 and then 1. Therefore, 0 is its minimum value, 1 is its maximum value. That is what the third property, if you see. Right? Now, I can give you the third property of the joint distribution function. Right? So, very plainly, if you listen carefully, you definitely will enjoy this subject. Right? The third property, I can write that. That means 0 is less than or equal to f of x comma y, and in bracket x comma y is less than or equal to 1. This is the third property of the joint distribution function. Means that what so the distribution function will exist between 0 to 1. This is the lower limit or minimum limit of the joint distribution function. This is the maximum limit or upper limit of the joint distribution function. Clear? That is the very important property. And there is one more property, that is fourth property of the distribution function is, say for example, it is non-decreasing function. You write like this, f of x comma y of xy is a non-decreasing, it is a non-decreasing function. It is a non-decreasing function actually. Means that what it is an increasing function. It is an increasing function. Right? It is an increasing function actually. It will never decreases. So that is what the property. Clear? I think we will finish off this presentation here. And with this, I think these are what a few important properties of this distribution. And one more property is also there, the fifth property actually. This is nothing but f of x comma y, in bracket if you say small x comma, if you take the plus infinite, so small x will be there, and instead of minus infinity, if I take the plus infinity, then it is obviously it is nothing but it gives your fx of x itself. Right? So f of xy is equal to f of xy in bracket small x and infinity, that is nothing but fx of x. And similarly you can write there is one more combination, f of capital xy in bracket small, y comma, okay, it is something like this, it is infinity, x is infinity, here y actually. So just reverse of this, okay, reverse of this actually, infinity comma y, this is nothing but your f of y comma y. What So from this, these are called, this is marginal distribution. This is called marginal. This is called marginal distribution. We will solve some few examples after 2 to 3 presentations. So marginal distribution of x, marginal distribution of x, and this is called marginal, this is called marginal distribution. Clear? This is called marginal distribution of y, random variable y. Clear? So sometimes in problems it will be asked that function will be given, find out the marginal distribution function or marginal density function, like that also they will ask you the questions, I think, because it is very nicely we must to able to understand, because if you go through very slowly and very clearly, then you definitely will understand it and you will enjoy it, right? So okay, so with this we will close today's presentation here, and will be continued in the next presentation with the properties of the joint PDF function, and then we will see some more important questions, okay, some examples based on these distribution density functions, and how we can check the given distribution function or density function or the valid distribution function as well as density functions, right? Okay, thanks for watching this video, and we'll meet in the next presentation. Have a nice day.